Good afternoon, everyone, and welcome to the ECE Senior Project presentation for the Northrop Grumman Collaboration Project, or NGCP for short. My name is Jeffrey Hymas, and I'm the project manager for NGCP. And we're going to be talking to you guys today about sort of all the contributions we've made as ECE majors to the project. Before we begin, I'm actually going to start by going over a brief project introduction and mission breakdown. So this is kind of a unique situation as far as senior projects go in the ECE department. So I want to make sure I get everyone up to speed on what NGCP is and what we're doing. And then we'll get into the actual technical review where we start going through the designs and the work that we've done. So in terms of the overall project, it's been ongoing for 10 years with direct support from Northrop Grumman, both financially and with advisors and mentors. We work collaboratively with Cal Poly SLO, so they developed one of the vehicles on their campus. We will not be talking about their work today because none of our senior project members work on their team, but I want to make sure that we pay credit where it's due because they do a lot of good work for this project as well. The primary goal of the project is to develop autonomous systems. Primarily this year, we're looking at aerial vehicles and ground vehicles. We also design our vehicles from scratch. We don't use any kits or anything like that. So that means that we have a huge focus on interdisciplinary teams. So we have majors from the mechanical department, Aero, ECE, CS, EMET, pretty much even business majors. They help handle the logistics side of things for us. So we bring a lot of talent from a lot of different areas of the campus together to try and accomplish the mission set forth for us from Northrop. A big part of that also is to replicate industry experience. That's something that we take a lot of pride in, is giving students the ability to see what it's like to work in industry and to go through a full design process, you know, while they're still in school, which is invaluable when you're looking for a job or when you're first starting out in your career. So that's a high priority for us. And so as part of that, Northrop provides us an actual RFP, which stands for Request for Proposal, similar to the one they would get from clients in industry. And it outlines our mission and outlines the vehicles that we have to build. And then we execute on that from essentially no design, just a mission statement, through all of the requirements and initial design phases, and then into actual development and testing, and then finally delivery and demo at the end of the semester. So it's a 2-semester project. We start in the fall, we end in the spring. This year, we're looking at 4 primary areas of development, 3 on this campus, 1 on SLO. So we are developing here at Cal Poly Pomona the unmanned aerial vehicle, which is designated kind of internally the multi-role aircraft, or MAC. We have the unmanned ground vehicle, which internally is referred to as the Emergency Response Unit, or ERU. We're also developing a ground control station, or GCS for short. And then SLO is developing a second aerial vehicle. The difference is our aerial vehicle is a fixed wing, blended wing. Theirs is a hexcopter, so this is vertical takeoff and landing. Not only do these vehicles have to execute their own part of the mission, but they have to interconnect as well. They have to be able to interact with one another, which I'll show in just a moment. So that adds another layer of kind of interesting challenge for us. It's one thing to build a single vehicle to accomplish something. There's another to get it to interact with other vehicles, on the field in real time. So that was another interesting element that we have to figure out how to deal with and overcome. In terms of mission this year, so we have an animation we put together so everyone has an idea of what the mission looks like. What Northrop has us simulating is essentially like a wounded hiker or someone in difficult to reach terrain who's not able to get out, and this system would be able to go in, identify their location via a radio frequency search. So they would have like any kind of radio that you could buy at Walmart or Target or whatever that broadcasts on the family radio service signal, and then would be able to deploy a vehicle to recover them and extract them to safety. So that's what we're going to look at now. So we have the air vehicle developed here at Cal Poly Pomona. We'll begin by taking off with the ground vehicle in tow. It'll execute a radio location search for where the hiker is. Once it's pinpointed their location, it will begin a drop sequence to drop the ground vehicle nearby. Once on the ground vehicle will begin GPS waypoint navigation to the hiker's location. It'll also be able to avoid obstacles in its path. Once at its location, it will be controlled manually by the ground control station and will recover the hiker, securing it on board, and then we'll transport them to an evac point. At that stage, the Cal Poly Pomona's part of the mission is done, and Cal Poly SLO's medevac aircraft, their aerial vehicle, will come in. The hiker will be handed off to them, and they'll extract them out to safety. back at our primary operating headquarters. So that's what the whole mission looks like this year. As you can see, it's a large mission. It has a lot of moving parts and several vehicles and being developed from scratch. So as part of that, we have a lot of development teams. On this campus, we have about 160 members. On SLO's campus, they have an additional 50 or 60, so we have over 200 people involved across both campuses. Our role as ECE members is, ECE students is obviously very specifically aimed at electrical, embedded, and software subsystems. So that's what we're going to talk about today. There's obviously a lot more to these vehicles. There's mechanical designs, aero designs, considerations for aerodynamics and payload and propulsion, all those things. But that's outside the scope of this presentation. We'd be here 4 hours if we were going to go over all that. So we're going to focus very specifically on these subsystems in this order. So starting with the ground vehicle, you're going to hear from Steve Paulin and Christian Jung regarding the electrical subsystem. Then Jonathan Juarez, Freddie Estrada, Raymond Bonda, and Minas Barbarian will cover the embedded system, which is going to talk about essentially how we go from software to hardware, that kind of stuff, the onboard computers, all that. And then Brendan Barrios will wrap up the ground vehicle section, speaking about their software design. We'll switch gears at that point, go over to the air vehicle, where Jacob Pollock will talk about the electrical design for that vehicle. And then we'll finish by talking about the ground control station, where Johnny Wilson will talk about the software design for the ground control station. And so with that said, at this point, I'd like to go and hand it off to Steve and the electrical team to begin the actual technical portion of the presentation.
So hello everyone, my name is Steve Paulin and I'm this year's electrical lead for UGV, and presenting with me is my sub-lead Christian Jung. We'll be covering the key areas of electrical developments that are integrated to the design of the UGV. Specifically, we'll be looking into the motor and battery analysis, a breakdown of our power budget, and the development of a PCB board to route power throughout the vehicle. Next slide, please. So first up is the block diagram, which shows the entire vehicle's electrical system. For us, we focused on the development of the overall power system embedded within the vehicle. So the power of the vehicle is routed from the battery into our fuel regulators, which will give us feedback on the remaining battery. From there, it will be then routed into our 5-volt regulator, our 3.3 volt regulator, and straight into the motor. Each regulator is sized large enough to handle the entire current draw of its own subsystem, and the motor is taking power straight from the battery as it's high powered. Following this, we'll look more into the sizing and analysis that was done to correctly size the motors. Next slide, please. Based on the requirements that are given to us from Northrop, the vehicle had to have the capability of being able to traverse a 40% grade hill at 1.5 miles per hour. First, we'll look into the speed requirement of that motor. This graph here is a torque versus RPM graph, where the y-intercept represents the stall torque of the motor, and the x-intercept is the no-load RPM of the motor. If you extrapolate a line between these 2 points, this line will allow us to find the RPM and torque of the motor at each point. The team found that the vehicle requires about an estimated 120 ounce-inches to traverse the 40% grade hill, and that is represented by the orange line on the graph. The point at which the orange line and blue line intersect can give us an estimate to how much RPM our motor will be producing at the required 120 ounce-inches. This is found to be approximately 103 RPM, which is about 2 miles per hour, assuming we have a 3.5 diameter wheel. This confirms that these motors have the capability of being able to meet the requirement of going 1.5 miles per hour. Next slide, please. The second half of that requirement is being able to traverse the 40% grade hill. To confirm that our motors have that capability, we found the motor constant KT, which is the ratio of torque per amps, as this will allow us to find the amount of current our motor will be pulling to traverse the hill. The blue line on the graph is the motor constant, which was given in the spec of the motor. The orange line again represents that required 120 ounce-inches needed to traverse the 40% grade hill. And the point at which these 2 lines intersect represents the amount of current we need to meet that required 120 ounce-inches. This gives us an estimated amount of 1.9 amps per motor, and with 2 motors, this puts us at about 4 amps for both motors to run. Therefore, the motor that was selected for the UGV is sized correctly for us to meet the speed and torque requirement of being able to traverse a 40% grade hill at 1.5 miles per hour. I'll pass this on to my sub-lead, Christian.
So another one of our mission requirements had our UGV travel a minimum of 1,500 feet after picking up the hiker. However, we also determined we needed to travel an additional 300 feet from the drop site to the hiker for a total of 1,800 feet. In the graph below, we show how we are able to determine the necessary battery capacity to power the vehicle. The x-axis shows the idle state after running for 20 minutes. And then as the vehicle starts to travel, our consumption of power would also increase, requiring us a minimum of 2,600 milliamp per hour to complete the 1,800 foot distance. Next slide, please. On this slide, we have a breakdown of our power budget of the 2600 milliamp hour battery that our vehicle would use. As you can see, the motors will be drawing the most power from the battery, which makes sense because the motor will be drawing the most amperage based off of our calculations prior, followed by our onboard sensors such as the GPS and the IR sensor. The processing unit, which is a Raspberry Pi, takes up a core of our power budget. And our retrieval systems, which consist of servo motors to pick up the hiker, takes up about 5% of the power budget. And lastly, the XP, which is used for communication, takes 2%. Next slide. Another one of our mission requirements specified that we needed to be able to repair our vehicle under 10 minutes. Due to this constraint, we thought it'd be beneficial to create a PCB power board that would step down and distribute the voltage to all the sensors. As seen on the 3D CAD model, there's a 5-volt buck converter as well as a 3-volt buck converter that can be easily removed through the connected mounting screws. To allow for quick repair, we decided to use Molex connectors that would give us plug-and-play access to each of the sensors in case we had to switch them during a failure or during a run. On the PCB, we also designed it with a copper backplate in mind to be used as a ground plane for the circuit, as well as a thermal dissipator to prevent overheating of the onboard components. Up next, I'll be passing it to the embedded lead, Jonathan.
Hi everyone, I'm the embedded lead, Jonathan Suarez, and I'll be going over the embedded systems for the UGV. You'll be hearing from myself along with Freddie, Raymond, and Minas. Next slide. So one of the requirements from Northrop required the vehicle to be autonomous and to have some sort of retrieval mechanism to allow the vehicle to retrieve the hiker. In order to ensure autonomous movement, we down selected parts. This includes the Intel RealSense camera, the IR sensor, and the ultrasonic sensor. The Intel RealSense camera is our primary object avoidance tool, with the ultrasonic and IR being the secondary in case of failure. We also include servos that will allow for retrieval of the hiker and external communication sensors that we'll go over later on in the slides. Next slide.
Hi everyone, my name is Minas, and I'll be going over communication protocols used with the Raspberry Pi and our sensors. So we started off using about 4 communication protocols depending on the sensors. So to start off, our analog to digital converter, the MCP 3008, communicates with the Raspberry Pi through SPI. Now this sensor was needed as the IR sensor itself is a straight analog sensor, which only gives us an analog output, and we cannot get that to communicate with the Raspberry Pi without this chip. And then following that, our IMU, our instrument measurement unit, which gives us a bunch of measurements for the UGV to use to make sure so we can track the status of the UGV. This uses I2C. We use I2C instead of SPI on this one because I2C was a lot faster, and we thought it would be better to use that to get the data better. Next, GPS and XV uses UART. This was the easiest to integrate into the system, and because the Raspberry Pi is a processing unit capable of UART and quick communication, this was best used with the GPS and XV. Now the other sensors all use digital signals, kind of just ones and zeros, especially our parachute and retrieval servos. These are just signals we need at certain intervals to know whether an event has happened or not, kind of like a check. And then lastly, our motor drivers, which send out PWMs. The Raspberry Pi actually would send out PWM signals to our motor drivers, which then ultimately will lead to the motors. Next slide.
Hi, my name is Raymond Banda, and I'll be going over the Raspberry Pi and its onboard processor. Next slide, please. The onboard processor, well, the reason why we actually, first off, we selected this, the Raspberry Pi was for its onboard processor and its capability in supporting multiple peripherals. So the Raspberry Pi 4 has a Cortex A72 ARM processor operating at 1.5 hertz, and it contains 4 CPU cores supported by common cache. Each of these cores is capable of running 1 thread, and it is capable of fetching 3 instructions per clock cycle. The Raspberry Pi also supports 40-pin GPIO headers that makes it possible to run all the peripherals that we are looking to run. And it's supported by 8 gigabytes of SRAM, which allows for fast execution of our instructions. It also can support powering up our peripherals through USB-C at 5 volts DC, or it can be supported through the GPIO header at 3 amps. Next slide, please.
Hi everyone, my name is Freddie Estrada. So when it came to using the servo motors on the Pi, there was a problem with latency coming from the GPIO pins on the actual Pi itself, which was causing the motors to jitter. So we decided to have a separate component dedicated for the servo motors, which is this Maestro servo controller. It has 6 channels, allowing us to connect up to 6 servos, and can also be used as GPIO pins if we want to. And it has a PIC18F microcontroller on board, which gives us the ability to interface it easily with the Pi and minimize latency. We could also run code to drive the servos, and it allows us to control position, speed, and acceleration, as well as configuring any pulse width modulation frequencies to meet any timing requirements. It also has, the manufacturer also provides a library in both Python and C for an easy software interface. In terms of communication between the servo controller and the Pi, it has 2 options, either through USB or through UART, which is another factor why we chose this component, because it gives us some flexibility to connect it to the Pi. Next slide, please.
As this vehicle is a part of a larger project, we need to ensure that information regarding our vehicle can be sent to every portion of the project. So in order to achieve this, we are using the XB. It's a communication device which will aid in communicating health and status or any other relevant data to GCS, as well as allow GCS to send location coordinates and signals for manual control. In addition, we're also including the Wolfel first-person view camera, which will be responsible for sending constant video feed to GCS. This will help in visual confirmation throughout the whole mission, as well as aiding in the manual operation during retrieval of the hiker when not directly in line of sight. Next slide.
So when choosing a board for our embedded side of the project, we looked into many different microcontrollers, microprocessors, and FPGAs. We did find that an FPGA paired with a microprocessor would have been an alternative for our system rather than just using a Raspberry Pi. But due to some resource limitations and costs, we decided it would be best to use the Raspberry Pi for the project design and continue working on the FPGA for research purposes. For the FPGA portion, we were able to accomplish writing our own custom IPs in System Verilog, which is essentially is to create our own hardware modules. And we were then able to interface it with the microprocessor using the ECE bus communication protocol, as well as deploying a custom embedded operating system on the microprocessor, which gave us the ability to download and install software development kits and access memory in the device address space. And I'll be handing it off to Brendan Barrios with software.
Hello, my name is Brendan Barrios, and I am a member of the software team for the Emergency Response Unit. Next slide. Our first task was to consider which development language that we were going to use. We were trying to find whether Python, C++, or C# was our main candidates because of the criteria of readability, the frameworks, writability, efficiency, and flexibility of the language given the project. We decided that Python would be the ultimate development language that we would use. It had the overall highest score, and due to its great support and its easy to use interface, as well as how it's built on top of C as a scripting language, we decided this was best for our rapid development needs. Next slide. This is the mission path that we are creating an API for using the Raspberry Pi and programming with Python. The first thing we have to do is connect to the ground control station. We're going to be using the XB in order to trade data, and we're using that as our transceiver. We need to be able to manipulate data and send it back using the serialized protocols. This was given to us by the ground control systems where they created an API for us to use, and we're going to be using the XB for that. From there, we move into the standby mode, which is essentially the hub for where we can move from any state in this path in case we need to move back or in case the mission changes for whatever reason, ground control has a way of moving into standby and then pushing on into a different state if that's needed. And then we do the landing sequence. As you saw in the animation earlier, we do have to decide when we're going to land and if we landed. So we are going to be sending signals, true false checks to ground control to make sure that we landed and that we were upright. So we will be using the IMU to make sure that our direction is proper. Then we have to autonomously navigate to the hiker's position. This is where much of the bulk of the work and where I'm going to be spending most of our time in the next few slides, because this is going to be the heart and soul of the entire ERU. We will retrieve the hiker manually. This was decided because trying to train a artificial intelligent or even trying to hard code an artificially intelligent robot to manually retrieve a hiker was very ambitious of Northrop to ask of us. So we decided to go with manual control inputs. And so we also have manual controls being developed for our inputs directly from the operators at ground control. Then we need to drop off for the medevac aircraft, place the hiker in the payload. Then we're going to move back to home base where we finish off our mission. Next slide, please. So this is waypoint navigation. This is essentially just a graphic showing one of the ways that we're thinking about the architecture of how we're going to be coding this. So we're always going to be receiving an input from GCS data about the location. This is going to be refreshed at about 1 hertz. And we're going to make sure that we are navigating using our compass. We have our obstacle avoidance that is running in the background to make sure that our path is clear. And if we need to maneuver around obstacles, we can do so. And so this is just a state graphic to show the overall architecture. Next slide, please. Similarly, this is specifically looking at the obstacle avoidance. There is a lot of contingencies, and we wanted a very robust system in order to be able to handle any of the obstacles that we might face out in the field. And I have a simulation for you in the next slide. So please, next slide. So this is a Weebots simulation. This is a physics engine simulation. You could see our small little car being controlled, and you can see actually a video feed in the left-hand side of the black and white what the car is seeing. You can see that it is deciding based off of that loop, that feedback loop of where to go. It's trying to navigate to the upper right side. It's very hard to see, but there's a white square amongst the brown checkering. And so the robot, the ERU, is trying to get to that waypoint, and that is basically our destination. So this is just a simulation of how the robot and the ERU is going to be autonomously navigating to a specific point, along with deciding how it's going to get through there and navigate through obstacles. Okay, I am done with my portion, so I'll be handing it off to the next team for, I'll be handing it off to the next team.
Thanks, Brendan. Hi, my name is Jacob Pollock. I am the electrical team lead for the UAV. Today, I'm going to talk a little bit about our electrical hardware architecture, power budget, and then we're going to dive right into radio location. There's so much more I'd love to talk about, but I think this is the most critical. Next slide. As you can see here, this is our electrical hardware and integration architecture. The UAV needs to do many different things, including carrying a payload. It needs to autonomously navigate and find the hiker using radio location, and it also needs to send data back to the ground on the health and status of the aircraft. You can see that at the very center, we have our processing unit. That's going to be a PC stick and a Pixhawk 2.1. These are going to allow us to autonomously navigate around our airfield. What I want to point out is that we have some new additions on board the aircraft that'll allow us to do health and status. That's a payload breakaway sensor to let us know if we've dropped the payload, a temperature sensor to let us know if things are overheating, and a voltage sensor that's just going to let us know if our engines are going to draw too much power. Next slide. Here you can see the power budget of just our avionics tray. I chose to exclude the power budget for the engines because they would take up my entire screen. As you can see on the avionics tray, the things that are actually going to consume the most power is our onboard PCs, and of course our 5-volt regulators distributing power to various sensors. Next slide. The primary focus of the electrical team, though, on the UAV has been radio location. There's many different applications you can use to find a hiker, and of those methodologies, after conducting a trade study, we went with Watts and Watt. Watts and Watt utilizes an adcock antenna design. You can see something of an image like that on the right-hand side. It's just a series or an array of monopole antennas that's comparing the voltage and phase with a reference sense antenna. This is a common system that you actually see used in the Coast Guard to find sinking ships or in radar. It's suitable for a family radio service frequencies, and it only allows us to find the incoming angle of arrival with just a short signal duration, making it ideal for our scenario. Next slide. Watts and Watt is just a methodology. We need to get this information on board so we can actually use it. You can see this is where GNU Radio comes in. GNU Radio is an open source signal processing software that we use to interpret these signals. On the left, we have an antenna array, and that's going to go into our Realtek radio module, which is just an FPGA. And then it's going to port this information into a PC stick. And I'm going to show you what this looks like on the next couple of slides. Next slide, please. So here's actually what GNU Radio looks like. This is our code, and this is just an example used to find signal strength. We have our RTL SDR source, that is our Realtek radio, bringing in an incoming signal from our antenna array, and then it's converting it into a magnitude value. We filter it, sample it, and then we send it off to a GUI sync, which looks like this. Next slide. This is it. So as you can see, this is not what the aircraft will actually see. We're going to send those values back out. But this is a real test of us measuring signal strength for our radio. You can see when I turn on the radio, our fast Fourier transformation plot at the very bottom is going to have a power value centered around 462.5 megahertz. That would be like the hiker trying to yell at you, asking for help. Next slide, please. And of course, once we have that information, this is what the calculations would look like. You can see this is an angle of arrival calculation. We have various voltages coming into our antenna arrays. And then after running through our scripts, we can find the incoming angle of arrival of the walkie-talkie. And with that, I'm going to hand it over to our ground control station team, led by Johnny Wilson. Next slide.
Thanks, Jacob. I'm Johnny Wilson, and today I'll be presenting our work on the ground control station. Next slide, please. The GCS is the center point of communication and control throughout the mission and acts as the primary interface between the operator and the vehicles. Next slide. The hardware that makes up the ground control station will be a central computer with 2 viewing monitors, an XB network node, a wireless video receiver with dedicated display, and a game controller for manual control of the ERU. Next slide, please. The primary programming languages used to develop the system were JavaScript for front-end development and Python for data processing and handling. We also use Python as our primary language for the communication system because of the readily available XB library. Next slide, please. Here we can see the GUI's main screen. It contains a large map of the mission area with which the operator can interact with by drawing geofence zones for the vehicles. All the vehicles' current location will be shown on the map in real time. To the right of the map is the current mission state and health and status information for all vehicles, including vehicle messages. There's also some basic vehicle control available, such as controlling the vehicle's state or mission state and an emergency stop button. A tab header at the top of the display allows you to see a more detailed vehicle-specific page, as well as return to the main page. Next slide, please. On the vehicle pages, we traded some of the map display real estate for detailed and vehicle-specific control windows. For instance, on the MEA and ERU pages, there's a control window for evacuation zone coordinates, whereas the MAC would have search area and ERU drop location input windows. Next page, please. This slide is a visual representation of the data transfer integration process. To integrate front-end and back-end and front-end, we used Python Flask API server to handle posts and GET requests from routes specific to each vehicle hosted on a local server on a single computer to pass data between backend and front end. Moving along the top arrows, GCS receives vehicle data via XB, then translates that data into a Python structure, which then is stored into the Flask API server for additional processing. The JavaScript UI will receive the vehicle data through GET requests from the server and finally display it to the GCS operator. Now moving along the bottom arrows, the GCS receives user-defined vehicle commands through JavaScript UI and updates the Flask server using POST requests. When the Flask server identifies a change in the user commands, it will encode the information into an XB structure before sending it out to the vehicles. Next slide, please. Now let's take a look at the communication system. The entire system's communication network is made up of 900 megahertz XB modules that have been configured to create a mesh network using the DigiMesh protocol. Using 900 megahertz modules allows for us to avoid interference in the 2.4 gigahertz Wi-Fi band, and the mesh network ensures constant communication by allowing each vehicle to be a relay point for any other vehicle's network communication. The XB modules also have 128-bit AES encryption for all communication over the network, as well as built-in acknowledgement system that we will be utilizing. Next slide, please. As for the transmission properties, the point-to-point bandwidth of the RF transmission is 156 kilobits per second and is decreased depending on the amount of hops in the transmission. Next slide. The packet format for communication is standardized for all vehicles and has a variable length between 50 and 200 bytes, and manual control data is encoded into the payload of the packet. And with that, I'll hand it back to Jeff Hymas.
Thank you, Johnny. So that actually concludes the technical portion of the presentation. I want to take a couple minutes here at the end just to update on the current status and future work of the project and to make some acknowledgements at the end. So currently we're in the manufacturing and testing phase. We're basically just building and testing stuff as fast as we possibly can. We've done flight tests for the air vehicle at 30 and 50% scale and currently manufacturing the full scale. We've done ground testing for the ground vehicle that include electrical tests, navigation tests, and working towards drop tests on kind of a separate chassis. Our delivery date is currently May 30th, so we're actually going to be working into a little bit into the summer to finish up the project. We're confident we're going to be able to meet that date. It's a lot of work to do, but we're making a lot of headway. In terms of future work, as I mentioned at the top, the project is ongoing. So we will wrap this year. Northrop will provide kind of a new mission challenge for us, and we will continue into next year. A lot of times that involves iterating and improving the current designs, adding more functions or improving the existing functions. Other times, Northrop has us sort of restart from scratch and build new vehicles, and we use the knowledge base from the previous years to help inform the designs of those vehicles. So we're not sure what's to come, but it's going to be interesting, and I'm sure you'll see more presentations from future ECE students using this as their senior project. I'd also like to take a moment to say thank you to some groups and people for their help on the project. First and foremost, the different development teams and project members without whom this project would not be possible. We have the UAV, UGV, and GCS teams on this campus, totaling 160 members across 7 different departments, 7 different majors. So thank you to all of them for all of their hard work and dedication. To SLO, who's does their own development on their campus, but who play an important role in the project. Thank you to them as well. Our faculty advisors, Dr. Zeki in the ECE department, Dr. Bhandari in Aero, Dr. Tang in computer science, Dr. Voskovich in EMET, and Dr. Castro in mechanical. Obviously Dr. Zeki is particularly important for the ECE majors as a advisor, but all of them are indispensable and have helped keep us on the right track and helped guide us in the right direction when we're trying to figure out the best way to proceed. So thank you to all of our great faculty advisors, and to Northrop Grumman, who has provided as I mentioned earlier, not only financial support but also reps and mentors to us. Thank you to all of them. Too many to name here, but a couple of people that I'd like to name specifically: Nicole Curtis Brown, who's our primary point of contact and is really responsible for the project being what it is today. And then also Norm Eng and Nolan Tanaka, whose support has been invaluable and have ensured that this project continues year over year and will continue into the future. And with that, that concludes this presentation. So thank you for attending. Normally, if this was not in a video format, we would open it up for question and answer. But if anyone does have any questions they'd like to follow up with, they're welcome to reach out to me. I'm more than happy to answer the questions myself or direct you to the appropriate people. Thank you. Have a good day.